Hello, in this lesson we're going to be looking at continuity at a point. So our outcomes are going to be to explain the three conditions for continuity at a point and describe the three kinds of discontinuities. So as we look at, we have three types of things that we want to happen for a function to be continuous. So looking at this first one, would this be continuous? And by continuous we mean it. If you were to draw the graph, you never have to lift your pen or pencil up from the paper to draw it. Well, right here, no, we have a hole in the graph, so that's not continuous. We have a place where it's not defined. In the second case here, we would draw along the line and then we have to jump up and continue up at another location. So this is not continuous because these limits from either direction are not the same. They exist, but they're not the same from either direction. So this does not have the same limit from each direction. And in the third case, you want that limit. So here the limit does exist. This is the same thing from both directions, but it's not the same as the defined value at that point. See, it's up there. So this limit along the line exists at A, but it's not the same thing as f of a. And so these are the three conditions we really want when it comes to finding out if something is continuous. First of all, it has to be the value itself has to be defined. We can't have a hole there. The limit from each side has to be the same. And then the limit that you come up with from each side has to be the same as the defined value at that point. So if not all three of these are in existence, then it's going to not be continuous. We call that discontinuous at a point. Okay, so how do we check that? Here's a little breakdown of the three steps. Check to see if f of a is defined. If f of a is undefined, we need to go no further. The function is not continuous at a. If f of a is defined, then go to the next step. Compute the limit of f of a. In some cases, we may need to do this by first computing the limit of f of x as x approaches a from the left, and the limit of f of x as x approaches a from the right. If the limit of f of x as x approaches a does not exist, that it means it's not the same from both directions, then the function is not continuous. And we're done. But if it does exist, go on to step 3. Now find out what f of a is and compare that to what the limit of f of x is as x approaches a. If those aren't the same, then it's not continuous. If it is, then they are continuous. So here's our first one. Is this one going to be continuous at x equals 2? So if I were to look at this, and just talking about the graph of this, we've seen this problem come up a few times. This x minus 4 over x minus 2 is equal to x minus 2 times x plus 2 over x minus 2, and you could divide out an x minus 2, and the graph would essentially be the graph of x plus 2. Just going to roughly draw a graph here. And what happens? We have an intercept of 2, a slope of 1. It's going to go along, but at this point here, at 2, 4, we would have a hole because of that x minus 2 that we factored out. So this is not continuous because of the hole. Okay. How about the next one? Is this going to be continuous? So using the definition, let's see, we have This f of x equals negative x squared plus 4, so that's a parabola that opens down. We're talking about the change occurring at 3. And so let's see here. It's going to peak here at 4, and then at negative 2 it's at 0, at 2 it's 0. It's going to be going down like that. And at 3 it's going to be negative 5, because let's see, negative 3 negative of 3 squared, that's negative 9, plus 4 is negative 5. So I just got to draw a few more of these. 1, 2, 3, 4, 5, and it's going to come down to this point here, and then it's a piecewise function. So what's going to be the other one? Let's see, 4 times 3 minus 8. 4 times 3 is 12. 12 minus 8 is 4, isn't it? So at 3, it's going to then jump up to the 4 mark, but it's an open circle there because for that one it's not defined. And then it has a slope of 4, so it's just going to be going up like that. Now this one, obviously the limits from either direction are not the same. So the limit as x approaches 3 from the left of f of x is going to be negative 5, but the limit as x approaches 3 from the right of f of x is going to be 4. So this is not continuous. Okay, moving on here. Now we saw this one, this sine of x over x, and that it's interesting because this is not defined at 0. But if you recall, when we did this earlier, our limit as x approaches 0 of sine of x over x was 1. But if you remember the graph of that, it came up like this, then we had a hole, and then that hole was at 1. But this one also then defines it as a piecewise function, so that at our f at 0 is 1. So here we have a case, so that hole created by the sine of x over x would actually be, filled in, because it's not a hole here, it's not undefined, because we defined it x equals 0, it is 1. So we don't have a big skip, a big jump, we don't have a hole, and we have that the limit as x approaches 0 of sine of x over x equals 1, which equals f of 0. So the limit exists, or it is continuous, I should say. Yay. There's a video for you to watch in the textbook. So here's another one. Using the definition, determine whether the function, it's a piecewise function again, is continuous at x equals 1. So what we're going to look at is the behavior on each side of x equals 1, and are those limits going to be the same thing, and are they going to be 2, because at x equals 1, f of x is 2. So we have, maybe we can graph it if we want, but I'm going to look for 2 times 1 plus 1, that's going to be 3, that's the top one, and the negative of 1 plus 4 is 3. So from either direction, it's going towards this 3. However, f at 1 is going to be 2. I mean, we have the limit as x approaches 3 from the left of f of x is 3, and the limit as x approaches 3 from the right of f of x is 3. But, oh, it's not 3, it's 1. Sorry about that. But at 1, it's 2, so this limit does not exist. Oh, sorry, the limit does exist. This is not continuous. Okay, let's try another one here. The question is, we're going to go through these steps here. What is f of negative 5 defined? F of negative 5 is defined here. It's going to be 2. So check that off. Does the limit exist for this? So our limit as x approaches negative 5 from the left of f of x is going to be, from the left, it's going to be that 5 times negative 5 plus 28, or 3. And then the limit as x approaches negative 5 from the right of f of x is going to be the square root of negative 5 plus 14, which is the square root of 9, which is 3. So our limit as x approaches negative 5 is going to, of f of x is going to be 3. So that works. Limit exists. Now the next question is the limit as x approaches negative 5 of f of x is the same of f of negative 5. Well, the limit as x approaches negative 5 of f of x is 3, but that's not the f of negative 5, because f of negative 5 is equal to 2. So our limit, or sorry, I've been doing limits so long, this is not continuous, because the limit does not match the defined value. Okay, let's go on here. So we have a polynomial function. We have to look for that denominator to make sure the denominator is not 0, because it's going to be a point of discontinuity. Recall the domain of polynomial rational functions. The domain of every polynomial function is all real numbers. The domain of a rational function can be found by setting the denominator equal to 0, solve to find the values of the variable that cause the denominator to equal 0, and the domain contains all real numbers except those where the denominator is 0. So for what values is this not continuous? Well, let's look at x minus 5 equals 0, so it's x equals 5. This is not continuous at x equals 5. Try the next one. For what values is this continuous? Well, that's a polynomial function, so by that previous definition, this is continuous for all reals. Now, we've seen these already, but we're going to put a name to it now, these types of discontinuities. So in the case that you have a hole, but it's defined someplace besides at that where that hole is, that's a removable discontinuity. In the case that it jumps, we call that, surprise, surprise, a jump discontinuity. And in the case it's approaching a vertical asymptote, we have infinite discontinuity. Okay. So what would this one be? Well, we saw this one earlier. If you recall the graph of this, it looks something like this. And at 2 it had a hole. So this one would be a removable discontinuity. In this case, let's see, the change is at 3. So if I look at the limit as x approaches, oh, we saw this one earlier. If you recall, this one had a graph that did the following. It came up and came down like that, and then it picked up here and went on. So that would be a jump discontinuity. And how about this one? Well, is it continuous at -1? Well, -1 is where we have 0 in the denominator. So we would have a graph looking something like this. That's a vertical asymptote. And I believe this would be going down here. There. So this would be an infinite discontinuity. And there's another video to watch, and then here's one more thing. Decide whether f is continuous at 1. If not, classify the discontinuity as removable, jump, or infinite. So here we have our limit as x approaches 1 of f of x, or of x squared. I should say just of f of x. But it is x squared that we're going to be plugging things into. So that's going to be essentially x squared let me just write it like this. That's 1 squared, which is 1. That's our limit for the x squared portion. Our f at 1 is defined to be 3. So what we have here is a parabola. It's coming down like this. It's going up, and then there's a hole. Then it keeps on going. Oops. There. And then at that 1, it's going to be up here at 3. So this would be a removable discontinuity. And that's it.